just shout at me if you have questions or it's just too much known. So I will try to keep left and right columns where left will be for algebras and right will be for groups. So if we have a Lie group, now its Lie algebra is of course given by the tangent space at the identity. Let's call it factor G, and the Lie bracket is given as the you take, let's say, for example, the left invariant extensions of the vectors into vector fields. You compute the Lie bracket of the commutator, and then you restrict this to the identity. Okay. And I say Lie group, Lie algebra. For this talk, it would be better to say algebraic, or maybe formal. We will see more of that in a few minutes. But I think at least in the beginning, it's just easier to say things for Lie groups. Probably also depends on your background. Okay, so if now we want to have a Poisson structure on the Lie group. And of course, and you will probably want some kind of compatibility with the Lie group structure and the Poisson structure. It turns out that essentially, if the Poisson structure comes from the fact that you see G as some sort of phase space, of a classical theory, classical physical theory, then like maybe like what you would write if you don't know anything, you would want the Poisson bivector is G invariant. But this condition, like this, or if the Poisson structure comes from being a phase space, it's a different condition, and it can write it as this. So I will write it in two ways. One of them is that the multiplication on the group, say mult, G times G to G, should be a Poisson map. So that's a different condition. Yeah. It kind of comes from the fact that if you recover this multiplication as a graph of some Lagrangian or quasi-topic submanifold, then the map will be Poisson. It's kind of a physical reason why you want this, let's say, slightly surprising condition. A different way to write is more down to earth. Right, push forward goes from the tangent space at H to tangent space at GH. So this is the condition. This is the same as this being a Poisson map is equivalent to this condition. I think I will need this, so I will call this 1. Special case, if we put G and H equal to E, we get that P pi E is equal to pi E plus pi E. So pi E is 0. Okay. So this are there questions? Yeah?
Could you briefly say what G?
Sorry?
Could you briefly say what
yeah, good, sorry. So pi G is yeah, I didn't say this very well. So pi G is a Poisson bivector. So pi G is a section of the second wedge of the tangent bundle. So locally, you know, it looks like pi I J d I d wedge dj, and this is antisymmetric. And it induces a Poisson bracket on the functions on the group by pairing with the differentials on two functions. Okay, thanks, yeah. The Lie bracket comes kind of from the multiplication. It sees only a small part of it, but you know, as you know, actually captures almost all of the group. Now there's a question if you can transfer this Poisson bivector into something on the Lie algebra. So yes, and it goes as follows. So if you take alpha and beta being two one forms, okay, then we can feed them into the bivector, right? We can compute pi of alpha and beta. This vanishes at the identity because pi vanishes at the identity. But you can compute this differential and then restrict to the identity, so this is an element in T star E of G, which is by definition, right? It's the dual of the Lie algebra. Now let's write it in some coordinates. Right, pi has some coordinates, pi j, and then alpha also has some coordinates. It's this contraction. And then we take dx k d over dx k of this. Right. Now if we differentiate, we have three terms. But if you don't differentiate the pi, and then you restrict to the identity, you get 0. Because the value of this tensor is 0 at the identity. Only its first derivative is non-zero. So there's only one term in this expression is this, right? So maybe I said that this is equal to this. So what we see that this only depends on the value of alpha and beta at the identity. So these are one forms, and these are really, so this really depends on the element in T E star G. So what we get is a map T E star G wedge T E star. So we get T E star G. Okay. That's question. I guess you have seen this. If you but please, if you have questions.
This would be some kind of Libra bit as well.
Yes, so there are two. Exactly, it satisfies kind of two more interesting properties. One of them, it's a Lie bracket. As I've told you, this comes from the fact that this is a Lie bracket, or plus minus, this is a Lie bracket on one forms on a Poisson manifold. So this is a Lie. So this map, let's call it delta transpose. So delta transpose is a Lie bracket. And the equation 1 here, it also gives you one additional condition. The so-called cocycle.
The thing is that it's a Libra bit of the dual.
Yes. Thank you. Maybe. So what we have in total, maybe it's good to say the definition. Lie bialgebra G bracket and a co-bracket is Lie algebra G with, so instead of this transpose, we use the transpose of the transpose, the original map. So this will be a map from G to G wedge G. And now this definition is correct also in infinite dimensions. Before I was kind of going between. Now it's good for infinite dimensions, such that which is a Lie co-bracket. But it just means you write the Lie algebra axioms in the opposite category. And it satisfies the cocycle condition, which I can write down as I hope. And this way, from a Poisson-Lie group, so this is a Lie group with such Poisson vector, it's called a Poisson-Lie group. Maybe I'll write it here. It's a Poisson-Lie group. And a Lie group with such a Poisson-Lie group gives you a Lie bialgebra. And by a theorem of Drinfeld, this is an equivalence of categories between Lie bialgebras and one-connected Poisson-Lie groups. This is a categorical I just say in words that there can be multiple groups having the same Lie algebra, but if you say it's connected and simply connected, it's good. Okay, so one can tie these two notions together. That's what also we want to do by talking about so-called Poisson algebras. Some people definitely know this well. Okay, so here it's quite easy. If we take functions on the group, and I will be more precise by which functions, but for now is not too important. If you take functions on the group, I guess you all know functions on a group form a commutative of algebra. Commutative. So maybe I will say it like this. So if G is a group, this is a commutative of algebra. Maybe, so if we are talking about, say, about Lie algebras or the tensor, so okay, the co-product which comes from the group product is the transpose, so it will give you a map from functions on G to functions on G times G. So this should be in some completed category because you want it goes to the completed tensor product. Okay. Maybe in topological vector spaces with some completed tensor product. So this, in general, you can talk about Hopf algebras in symmetry modular categories. If G is a Poisson-Lie group, what you have in addition is the Poisson bracket. You have a commutative algebra. You have a Poisson bracket. Right? And being a Poisson bracket, there is some compatibility between the bracket and the multiplication of the Hopf algebra. Right? It's about the Leibniz rule. Okay. This is compatibility. So compatibility with the product structure. And there is one compatibility with the co-product coming from here. And you can say that the co-product, which is the transpose of the group multiplication, or maybe let's say multiplication pullback, is a Poisson map. Okay, I think I've managed. So I draw diagrams from the bottom to the top. So if this is the Poisson bracket, and this is the co-product, and this is the M is now the product of the Hopf algebras, the commutative product. Okay. And you read it from the bottom to the top. Yeah. You can get the same object on the right-hand side. So let me explain why, how. So okay, first, here we had to take functions to get at least some kind of algebra. Here we take UG which is a co-commutative of algebra. This means it's a commutative of algebra in vector. Commutative of algebra in the opposite category of category vector spaces. And it also has a Poisson bracket in this category. So if you look at this axiom in the opposite category, then tells you that P, it should be a map. Poisson bracket is a map from Hopf, tensor Hopf to Hopf. In the opposite category, it goes from Hopf to Hopf tensor Hopf. It's actually anti-symmetric in the target. And it satisfies that P on xy is equal to px times delta y plus delta x times ey. Delta is the co-product. Maybe let me put some, let's call this p tilde because it's a different map. So you see that you only need to give p on the generators of your universal enveloping algebra. There you just use the co-bracket, right? So we have a map from, so p tilde is, you go from G to G wedge G. Okay, sorry, maybe I can say it here. So this was for a Lie algebra, and now we want to start with a Lie bialgebra. And for a Lie bialgebra, you can do this construction. Go from G, you use the co-bracket to go to G wedge G, and then you include both of them into G. And then you extend by this rule. Okay. So both of them are objects of the same kind in different categories. They are connected by the following duality. I guess one could call them classical duality. You have a pairing between UG and functions on the group, and we are getting close to the point where we actually have to think what kind of functions on the group we use. Not yet. So, right. Okay, so if you have first, if we have an element in the Lie algebra, we can pair it with a function as follows. It gives we have a map. Sorry, a map from the Lie algebra. Let me write it like this. To home from functions on the group. Okay, let's say everything is over complex numbers. They're not important at all. And it sends, X is sent to a map, which sends a function f into XLF at E, which is like d over dt. You can differentiate the function with the what's in the vector field and then restrict to 0. If you start with UG and you have x1 until xk, you send it to a function which sends f to x1 L to the xk L of E. So we now act by a higher order differential operator. So what people say, right? We see UG, we see as distributions. But they are supported as the identity of the group, which means that they only really depend on the value of the function at any neighborhood of the identity. Okay. Because you just take the function and its derivation, and then always you evaluate the identity. Okay. And this gives you a pairing from UG tensor OG into C. Okay. And now comes the point we have to think about what kind of functions we we talk about. What functions? So I guess what kind of functions such that the pairing is non-degenerate, such that or it's perfect, such that you can distinguish two different functions by its values from pairings with different elements. Pairing. So definitely we can distinguish. Let's think in some coordinates. We can distinguish polynomial functions because you can kind of like by taking smart enough derivatives, you can isolate like the coefficients of the Taylor of the polynomial. Polynomial is definitely good. But you cannot distinguish smooth functions because if you have one smooth function, another smooth function, and you deform one of the two smooth functions, if you deform a smooth functions away from the identity, it doesn't change any of these values because this only sees kind of derivative of the identity. So C infinity of G, no, this is not good. But you can see more than polynomial. You can see kind of like all power series, and that's the kind of the setting also we'll see in the talk. And so what is the correct O of G is to take the formal functions. So which means precisely is that you take algebraic functions and then you complete at the ideal which is given by the kernel of the counit. More down to earth, you choose some coordinates centered at the identity. Sorry? Oh, centered at the unit. And then take formal power series in those coordinates. And then take formal. Sorry. So what we get here is, what we get by this is something called a formal group. Which is, you would call this the spectrum of some power series ring. And now you have a multiplication, and multiplication is given actually of the group, which is given by a co-product. So you have people encode it. Something which is called a formal group law. So this is a formal group. So you have algebra of functions which look at formal power series and some variables, and then the multiplication is given by like this. By something called formal group law. For example, SLN delta of, you have functions which look like rho ij, so matrix values. They have there's a relation that the determinant is 1. And you have this is the formal group law. Okay. 4 minutes. Yeah. So I can talk about quantization now. Oh well. Maybe let me start here. Oh, okay. Let me do it in a different way. Sorry. So now there are new definitions, which are the quantum counterparts of the Poisson-Hopf algebras on this board. So on the left, we have something called the quantum universal enveloping algebra is, by definition, a Hopf algebra over, so it's a module, what's it, in C power series in H bar. So let me introduce this notation. C with H bar is power series in H bar. There's a Hopf algebra in C H bar modules. Now I'm not sure if I need to say it with respect to the completed tensor product or that's not necessary. It should be in respect to the completed tensor product.
The algebra itself must be complete for the entire topology.
So that's why that I want to say. Such that A is topologically free CH bar module. So it means that it's isomorphic to V power series H bar for some V, for some vector space V. And if you take such a quotient, this is isomorphic to UG as a Hopf algebra. For some G. So this is maybe for so far this is only UG as a co-commutative Hopf algebra. The Poisson structure comes into play as follows. Okay, so let's say that this A has a coproduct. And because of this, if you choose some isomorphism, you can write it as delta 0 plus H bar delta 1 plus. And I guess you've seen this, if you have a deformation of a commutative product, the antisymmetry of the first order is a Poisson bracket. The same is true here. Is the co-bracket. On G. Okay, so making Lie into a Lie algebra, making G into a Lie algebra. Yeah, I guess that's what you were asking.
And if you look at G or UG, if you look at G,
Yeah, okay.
Because you were saying that, okay, for the product, we get a Poisson bracket, but I expect a Poisson bracket.
Yeah, okay, sorry. Which-
Right, but then in the universal,
Yeah,
possible.
Sorry, it is true what you are asking, and it's actually these two things are equivalent to each other. Poisson co-bracket on UG. So Poisson co-bracket is the same as a Lie co-bracket with the co-cycle condition.
Right, so you simply extend by this.
By the rule, yeah. There is a little bit more. You have to know that if you apply it on G, you still land in G wedge G. But this is true. Yeah. So okay, I guess the logic is that if you have such key quantum universal enveloping algebra, you see there's a formal deformation of U of G. And you can also kind of try to go do the problem from the other way. You start with UG, and then you also supply some kind of co-bracket, and you try to find a Hopf algebra which will give you back this structure. So that's the quantization problem. And I guess I'm over time, but when I let's say a little bit in in the quantum in the group case, the object is called quantum formal series of algebra. It was introduced by Greenfeld in the paper Quantum Groups. And we've already seen that on the classical level, this had to be topological. So this is even more topological, right? There is topology from being like formal power series, and there is topology from the H bar. So it's more topological. So this is A, which is Hopf algebra, and now it's a topological Hopf algebra. Over CH bar. And there's a slightly different condition that it's isomorphic to CH bar. No, so this is like an infinite product of CH bar modules. So this as CH bar module, where I is some kind of set. Okay.
Excuse me, because for me, it's
No, so I think it's a Hopf algebra in some category of topological vector spaces, and it has a structure of a module over CH bar, which is also a topological ring, and and the action is probably continuous.
No, the topology is not the same.
This has more topology, not. Okay. Okay, let me say one more thing. If you again reduce this modulo H bar, you get a formal group. Which is already a topological object. Okay, so there's topology remaining. And again, yeah, I do not even say this. You get a Poisson bracket by the obvious nonsense. Once again, sorry?
It's not the form B form of series H bar.
No, it's
And they say geometric topology, one given by the real the augmentation.
maybe I can say with saying that there is a duality between these two, like an exact categorical duality, but I think we will see more. Okay, thank you very much.
So, Jan, for the nice talk. Are there some questions? Maybe I can start with one. So can you maybe say some words how we get the nice Grünfeld Jimbo quantum groups? Because I guess they are hidden somewhere here, right?
Yeah. So Greenfeld Jimbo quantum groups, they exist for semi-simple or simple Lie algebras. A simple Lie algebra have a. Okay, I see. Okay. Okay, yeah. But so I guess it's true that also they have a canonical Lie co-bracket structure. And then those are quantizations of this canonical Lie co-bracket. And yeah.
And then you get some H bar.
Addict version of the usual Q.
Yes, sorry. So this I forgot. If you know quantum groups, you usually maybe know them with are defined with some kind of parameter Q. You say it's a number or maybe it's an indeterminate. These are actually they have H bar. If you have a Q version of a quantum group, you can always set. Yeah, I think always you can set Q equal to E, the H bar, which means that from a quantum group with Q in the definition, you get the quantum group with H bar in the definitions, and those are the Greenfeld Jimbo quantum groups are such.
Yes. More questions? Maybe from the online audience, if you have a question, just unmute yourself. Okay, seems not to be the case. Then let's thank Jan again.
Thank you.
There's a short break and then we have the main seminar.